Right, well, good afternoon or good morning if you're over here in Western Australia. Thank you for joining Rizzo and our latest webinar. Today, we're obviously looking at can diesel be net zero? A very interesting topic and certainly one that's very topical at the moment. Before I start, I would like to acknowledge the traditional custodians of the land of where we meet today. For me, that's in Perth in Western Australia. So I'm on the land of the Whadjuk Noongar people, and I'd like to pay my respects to their elders past and present. I'd also like to extend that respect to any Aboriginal or Torres Strait Islander people with us today. At Rizzo, the Australian Rail Industry Standards Organisation, our role is to work with industry and governments to support a safer, more productive and increasingly interoperable national rail network. A key part of that is ensuring the standards framework evolves alongside new technologies and emerging challenges. One of the major challenges facing the rail sector today is decarbonisation. Whilst rail is already one of the most efficient modes of transport, diesel locomotives and DMUs still account for about 1% of Australia's CO2 emissions. With the national goal of net zero by 2050, the industry is actively exploring pathways to reduce those emissions. Now, there's a lot of options here. Electrification, batteries, and hydrogen are all part of the long-term conversation. But for many rail services, particularly freight and regional, diesel traction will remain part of the system for some time yet. So that raises an important question. Can we significantly reduce emissions using the fleets we already have? Today's webinar explores whether renewable or alternative fuels could provide a practical pathway, allowing existing diesel locomotives to operate with much lower emissions and potentially at far lower cost than replacing entire fleets. We'll hear about a range of fuel options, including biodiesel, HVO, synthetic diesel, ammonia, methanol, and dimethyl, ether, and what that might mean for the future of rail. So today I would like to introduce our presenter, Frank Zanto. Frank is a mechanical engineer with over 40 years experience in the rail industry, having been involved in the design and manufacture of locomotives and passenger trains operating in every state of Australia. He joined us here at Rizzo after 3 years in consulting and is a graduate of the University of Sydney and a fellow of the Institute of Engineers in Australia. Frank, thank you very much for offering to present today. Before I hand over, I'd like to remind everyone, if you have any questions, please go to the Q&A button at the top of the screen and ask questions at any time during the presentation. When we get to the end, I'll present those questions to Frank and we'll see what he has to say. So that's enough from me. Now over to you. Thanks, Frank.
Okay, thank you. And thank you to everyone for joining the webinar today. I must say, I did most of the preparation for this for Osrail last year, and that was before the world caught fire. And at the moment, I wonder, does anybody care about emissions, or would they just like to get their hands on some diesel if they possibly can? But I think the talk is still relevant because looking at what are the alternatives to diesel fuel for diesel. So we'll go ahead. We'll keep going with the seminar. Okay, so rail emits 4 million tonnes of CO2 a year, 1% of Australia's total. And transport as a whole in Australia is 22.6%. So you think with such a small proportion, rail will get a free pass. Well, unfortunately, it doesn't. Under the safeguard mechanism, a lot of larger rail operators are classified as big polluters and are caught up in the safeguard mechanism, which requires that you reduce your emissions by 4.9% per year until 2030, or otherwise you have to buy carbon credits. And at the moment, there is no easy way to achieve this. Whoops, went too far. Okay, so our major cities have electrified suburban networks, and hopefully electricity is being slowly converted to renewables. But outside the big cities, rail is powered by diesel. And just in case you forgot, diesel is all imported. We don't make it in Australia. Diesel fuel, that is. So there's an existing fleet of about 2,200 diesel locomotives out there, and also 250 DMUs, that's diesel multiple units, that's individual carriages. So that's nearly 2,500 vehicles altogether. So what time period would it take to replace them when you think that if we've got to have them off by 2050, and like most diesel locos just go forever. Like there's a lot of diesel locos which are still out there, which were built when I was in primary school. So one thing you could do would be to electrify all of our rail networks. And we've got about 41,000 kilometres of track, of which at the moment about 3,400 kilometres is electrified. So just taking $5 million a kilometre, that would be $200 billion to electrify it all, which is a lot of money. So general talk is of using batteries and hydrogen as cheaper ways to electrify. As of today, the range of battery trains is typically less than 200 kilometres, so it's not a universal solution. Batteries are finally starting to be installed in locos in the Pilbara. Both BHP and Fortescue have taken deliveries of a few prototype Bell battery electric locos just in the last 6 months. And yeah, they're going to be commissioning them for quite a while. So the advantages in the Pilbara, like the distances are about right, 200 to 400 kilometres to port, and the loaded direction is mainly downhill. The mines are up in the hills, so you're going downhill to port and you're in regen braking most of the way. So that's advantageous for batteries. So they've got testing underway, but it's still going to be a long time before we see much movement in the composition of their fleets as they start to move to batteries. Outside the Pilbara, there's really not much happening in Australia at all. Horizon's converting one narrow gauge loco. That picture on the right is a battery pack used on the 3000 class rail cars in Adelaide, which have been turned into hybrids, mainly so they can just not use engines when they're idling in the station. But it would be expensive to convert all our fleet at the moment to batteries. If it was $5 million a pop, this is a figure from the air, 2,500 units, you're looking at $12.5 billion. And you'd have to convert 100 a year until 2050 to replace the whole fleet, that's a lot. And at the moment, batteries still can't go the longer distances. So the question is hydrogen the answer? Okay, so what I've got in the picture there is the refueling station for a fleet of hydrogen trains running in Germany. So this fleet was introduced in 2019. There are 2 car sets with fuel cells replacing these multiple units. But you can see that the infrastructure just to fill the trains is pretty significant. You've got all those high pressure reservoirs there, which store hydrogen at 50 megapascals. The hydrogen comes by truck on the road from a chemical plant 35 kilometres away. Transporting and storing hydrogen is very expensive. And at the moment, the hydrogen is actually made from natural gas or methane. When you make it from renewables, it's even more expensive. And the cycle efficiency from when you go you're making the hydrogen by electrolysis of water, then you're transporting it, storing it, then it goes into fuel cells, you've got a loss of efficiency there. You end up, it's about 25% efficiency over the cycle, so much less than for batteries. And there's really been no progress since 2019. There was a certain amount of optimism back then, but really nothing has happened with hydrogen since. And in fact, the idea of hydrogen-powered fuel cell cars, they're dead in the water. Toyota developed the Mirai and Hyundai the Nexo, and that development started more than a decade ago because at the time, nobody thought that battery electric cars could ever have the range that's needed to replace conventional petrol engine cars. But now, these are nice cars, but battery cars will do it for half the price or even less. And because there's been no development of hydrogen cars, nobody's built a network to refuel them. So there is no hydrogen fuel network. There's no hydrogen economy. Some manufacturers are still persisting with fuel cell trucks because they think hydrogen is the answer for long distance trucks. If they succeeded, you'd have to build a network for refueling the trucks, covering all over the state or the states. But until that happens, there's no incentive to build a distribution network. And with that demand, no one's going to develop this hydrogen economy. I really think it's going nowhere. So you ask the question, well, if only we could keep using our diesel fleet somehow. And what we really want is a drop-in zero-emission replacement fuel that wouldn't require modifying locomotives at all. And the first thought, well, vegetable oils, you can burn vegetable oil in a diesel engine. And in fact, Rudolf Diesel, his early experiments, he was using peanut oil. One of his first diesels was exhibited in Paris in 1900, running on peanut oil. And vegetable oils are they are triglycerides. When you burn vegetable oils in a diesel engine, it cokes up in no time, and that's not a good thing. Well, why did that jump forward there? So the answer to that is to make biodiesel, also known as fatty acid methyl esters, which you can make on a kitchen stove. It's quite simple. You heat up vegetable oil with some methanol, and you heat it, moderate heat. And that produces, and you can see down the bottom of the screen there, a FAME or fatty acid methyl ester molecule. And the triglycerides are just three of them side by side, joined at the head with the three carbons joined together. And when you boil it with methanol, the methanol replaces the three at the head. It goes away and produces glycerin. That's a byproduct. And you get this molecule, which is exactly the same as a diesel, as molecules in diesel, with 16 to 18 carbon atoms. But the difference is you'll see there's two oxygens over on the right-hand side. And that is a downside because that makes it hygroscopic, which is like normally oil and water don't mix, but biodiesel does. It will hold water in suspension. And that means when you store it for a period of time, because it's kind of a food, it grows all sorts of bacteria and all sorts of stuff, which turns it into a sludge, which is very bad for diesel engines. So you never see biodiesel being used at 100%. It's always in blends of 5 to maybe as high as 20%. And most diesel manufacturers won't even give you warranty with 20%. It's usually much lower than that. So biodiesel is only useful as a blend. And the answer to that is hydrotreated vegetable oil, HVO, where what it does is it takes that molecule and it strips off those two oxygens and turns it into just a pure hydrocarbon, which is exactly the same as a component of diesel. So it's like a very pure form of diesel, exactly the same formula. Trouble is, you can't do this on your kitchen stove. This requires quite high pressure and heat. It's an industrial process, so it's quite a bit more expensive than biodiesel. But there's a problem for both biodiesel and HVO, and that's the feedstock problem. On the left there, you can see some, I think they're dim sims or something, frying in some vegetable oil. Well, you always hear about it being made from waste oil, but there's nowhere near enough waste oil. We don't need enough fried food to provide fuel for our locomotives, let alone anything else. So we have to find a feedstock. Now, in the EU, they've had some scandals with palm oil where they like to have everything green in the EU, and they don't like rainforests being chopped down in Indonesia so you can grow palm trees and make palm oil. But the scandals were that palm oil was being imported to the EU labelled as mill waste, like the impure stuff that's when you start up and stop your process. But it turned out they were sending large quantities of virgin palm oil, which was not what was supposed to happen. So yeah, rail requires a lot of vegetable oil if we were going to go this way. Our annual consumption is about 1,700 million litres of diesel. So if you're going to replace that with oil, say from grain, you'd need 4.5 million tonnes of grain. And our whole canola harvest is about 6.5 million tonnes. And actually, apparently, most of that goes to Europe to make HVO. So with if it was just rail, you might get away with it, but road and aviation are going to be competing for the same oil, and between them, they're more than 20 times bigger than rail. And displacing food production for to make fuel, it's just a dead end. It's just not going to happen. We'd have to double all our grain production just to make fuel. So, and the other question is it even zero emission? Like to grow grain, you need fertilizer, and as we've just discovered recently, the ammonium-based products all come from the Middle East. They're made from natural gas. And also you need diesel for your farming machinery. So there's actually quite a bit of fossil fuel that goes into growing grain. So if those are ruled out, what about synthetic fuel made from biomass? By the way, that picture on the right is a grain train unloading at a grain hopper. So you can actually synthesize any hydrocarbon using the Fischer-Tropsch process, which was invented by some German chemists back in the 1920s. And it fueled the German war machine in the Second World War with synthetic fuels made from coal. And also, it was also in South Africa in the apartheid era when they couldn't get, when they were being boycotted and couldn't get oil. So it does contain exactly the same molecules as diesel fuel, but it actually, what comes out is a range of hydrocarbons, but you get exactly the same molecules as diesel. So it's good in that way. And in the US at the moment, there are trials, it's called gas to liquid, where they're making diesel from natural gas rather than coal, which is obviously still fossil fuel. And you could use biomass, or there's even talk of extracting CO2 from the atmosphere to make it. But that's a lot more expensive process. Using natural gas is the cheapest way of doing it, but it still costs about 3 times. It's still 3 times the price of fossil diesel as it is now. And for a lot of freight operators, fuel is about 1/3 of their operating costs. So if you were to use a fuel which is 3 times the price, your business is pretty much in danger. So if the drop-in fuels are too expensive and not really viable, what about the non-drop-in alternatives? So this table here it's not an exhaustive list, but most of the alternative fuels which are proposed. Now, the things that are coloured red means that's not good. So you can see on the left-hand column, most of them will not ignite in a diesel engine. They won't work in a compression ignition engine, except for, you see at the bottom, there's DME, which I'll talk about later. So that means you can use a certain percentage, but you need a pilot fuel to ignite the mixture at the beginning of the combustion stroke. The other thing is most of them are gases. There's a few liquid, and except for natural gas, they all have a lower specific energy than diesel fuel, some quite a bit less. So all of these will need engine modifications, separate fuel tanks and systems if you're going to use a pilot fuel. So the first one, ammonia, it's NH3. It's a true zero carbon fuel. Trouble is, at the moment, all ammonia, well, nearly all ammonia is made from natural gas or from methane using the Haber-Bosch process. So you don't give off CO2 when you burn it, but you give off the same CO2 when you make it. So there's certainly no advantage in that way. But you could make it you could make the hydrogen by electrolysis and then go through Haber-Bosch. So yeah, it could be made renewably, although it's a lot more expensive that way. But at the moment, there's a lot of interest in ammonia in the shipping industry because they've got to look at replacing their oil-fired engines in the future. So a lot of engines being developed to run on ammonia. Among the disadvantages, it's a gas. It can be liquefied at minus 33 degrees C. It's got very poor auto-ignitability and a slow flame speed. So it needs diesel as a pilot fuel. And in fact, if you convert a diesel engine, it needs quite a lot of diesel. So you might only be substituting 60% of your diesel in a converted engine. When you've got a combustion chamber that's specially made for ammonia, it can be, you can get it by with a lot less pilot fuel, but for a conversion, you need quite a lot. So you need a dual fuel system. And one of the other problems is you need high compression to get the ammonia to fully burn. And that produces quite a lot of NOx, nitrous oxides. So you need exhaust after treatment. If you have a lower compression ratio, so you don't produce as much NOx, then you get unburnt ammonia in the exhaust, and that's toxic. So your choice is being noxious or toxic, I suppose. And it's also quite a low energy fuel. So it's only about 25% of the energy by volume. So you're going to need, well, number one, you need to store it in pressure vessels rather than a box-like fuel tank. So you're probably going to need a tanker like the one on the right. They've used, that tank is for LPG, but they've used them for carrying ammonia as well. But on the whole, ammonia's got a lot of negatives, and I don't think it's a viable alternative for the future. There's LNG, methane. When fracking first started, there was a lot of interest in trying to get diesels to run on LNG, and both EMD and GE, as they were at the time, did quite a lot of development work and ran trials with several of the US major railroads running diesels converted to run on methane. The gas has got to be either compressed or liquefied to carry it around. And in spite of the trials, there was only one railway which adopted it in the end. That was Florida East Coast. They've got a fleet of 24 locos running up and down the coast of Florida. They carry, whoops, jumped again without me asking it to. The LNG, liquefied natural gas, it's carried in a cryogenic tank on a wagon, which is specially collision resistant because they're worried about being hit on level crossings. And it sits between two locos, providing fuel to each. So you've got, you have to have a lot of pipe work because you've got to regasify the methane, and they use radiator water from the diesels is piped back to this this wagon in the middle, and then there's heat exchangers. They gasify it, pipe it back to the locos. So it's not a zero emission fuel. It does reduce CO2, but only by about 28%. The substitution, so it's running on about 80% LNG, 80% LNG and 20% diesel. And in the US anyway, natural gas is cheap, but if you make it from methane, make methane from renewables, it's not so cheap. Now, I don't know why, it keeps jumping ahead. Anyway, I think that's the right slide. Let me just check. Yep. So that brings me to dimethyl ether, which you may or may not have heard of before. So it is made from, well, the usual part to make it is from methanol. So you basically stick two methanol molecules together. You can see the one at the top. The methanol is kind of like the three-legged dog. You stick two together, you get the push and pull you down the bottom. And it's got the same atoms in it as ethanol, except there's an oxygen in the middle between the two carbons. And that has the effect, it has a high cetane number, even higher than diesel, so it will work in a compression ignition engine, unlike methanol or ethanol. Sorry, this just keeps jumping. It has relatively low NOx, and also it has very low, or hardly any soot at all. Because of this oxygen between the carbons, it just doesn't produce soot. And it was originally investigated as a replacement fuel for urban buses because it means no particulates in cities, which was seen as desirable. So that was in the days before greenhouse gases became the overriding issue. But there is bad news, and it's a gas. So it's boiling points minus 25 C. It's very similar to LPG or propane, which you might be familiar with from barbecues and things like that. You get it in cylinders down at Bunnings. And when it's compressed, like at 500 kPa, which that's brake pipe pressure on a train, so it's not a really high pressure. It'll still remain liquid. at 20C. So I compare it like it's like a barbecue fuel compared to liquid hydrogen, which is rocket fuel and requires very high-tech handling. It's got some other disadvantages. It's got very low viscosity. This thing's got a mind of its own. Low viscosity, so it does wear out pumps unless you add a lubricant, and it does need new injectors because you need a higher volume of it than diesel, and it is lower energy density than diesel. So you do need to screw it more in. The fuel tanks need to be cylinders, not a box. So I've got a picture of a loco there with a 10,000 litre fuel tank. So in that space, if you put cylinders like packed together in that space, you can only fit about 4,650 litres in the space of 10,000. Well, sorry, the equivalent energy of 4,650 litres of diesel. So for longer journeys, you're going to have to tow a tanker. But as for making methanol from biomass, if you heat up wood without letting it catch fire, so in an oxygen depleted environment, you get what's called syngas, which is a mixture of carbon monoxide, hydrogen, some CO2, and a little bit of methane. To make methanol, you need a 2-to-1 ratio of hydrogen to carbon monoxide. So what they do is that there's what's called the water shift water shift reaction, where you inject high pressure, high temperature steam into the syngas, and that converts carbon monoxide, strips off the hydrogens from the water, so you get CO2 and hydrogen to get the right ratio, and then you can make methanol. So you could make the hydrogen by electrolysis using renewable energy, and that's that's the future path. And that means you produce a lot less CO2 when making your methanol. So, and then to make your methanol, make your DME, you join your two methanol. It just requires a bit of pressure and temperature to join them. And we would need the DME equivalent of 1,700 million litres of fuel, which we need per year. You need about 10 million tonnes of biomass. And that's not an out of the world quantity. We export about 12.3 million tonnes of wood chips, or we did in 2022, and that word for cane waste is about 5 million tonnes. So that amount of biomass is not unreasonable. The only problem is that if the road transport and aviation industries also go down the same path with Fischer-Tropsch and they're chasing biomass, there'll be competition because they need about 20 to 4 times more. But then the question is it really net zero? Because obviously you're releasing CO2 both when you make DME and then when you burn it. So doesn't that count? Well, just for perspective, in the really bad bushfires we had back in 2019, 2020, 830 million tonnes of CO2 was released just in that one summer. But that doesn't count on your school record because, CO2 from wood, which regrows, doesn't go on the official figures. So our official CO2 for that year was only 528 million tonnes. Here we go again. So you could take the point of view that why not harvest our NF spinator forest, please don't tell anybody, and then save burning all those marsupials because the bush is going to go up anyway. So why not just take the wood out first? But yeah, I won't mention that. That's not a good path to go down. But methanol is traditionally made from wood, but any biomass can be used. The other thing is you can actually use the methanol as a fuel without even making it into DME. But you do need a pilot fuel. And in fact, the other alternative to ammonia for ship engines is methanol. That's the other thing that there's a lot of engines being developed requiring a pilot fuel. But you can use methanol as the bulk fuel. It's relatively cheap. And use your more expensive fuel, your HVO or synthetic diesel or DME, you could use as your pilot fuel, which is only needed in small quantities. And being a liquid, methanol is much easier to store and transport. You don't need a pressure vessel. And it does have, its volume is less than DME, but you kind of, what you lose on the roundabouts, you win on the swings or around because you don't need to store in a pressure vessel. So that 10,000 litre tank I showed you in Loco before, you could store the energy equivalent of 4,900 litres of methanol, for 4,900 litres of diesel, the energy equivalent. So it's actually, you're slightly better than DME in that sense, but you still need, it's still only half the range of diesel. You probably need tankers for longer distance. And the other thing is with DME, you could just make it at the point of use where you're actually filling your locos, maybe, rather than carry it around on the road on trucks. So if you're going to take this path, you need to build a methanol DME ecosystem. So I'm imagining that maybe half of rail is going to go to batteries in the longer term. So maybe you only need to make enough methanol and DME for half the existing loco fleet. So you need about 1.3 million tonnes a year of methanol. At the moment, Australia makes no methanol. We had a methanol plant in Laverton, Victoria, closed in 2016 because natural gas was getting too expensive. But there is a company, Able Energy, who are looking to make green methanol in Tasmania at Bell Bay, using like forest waste and electrolysis for hydrogen. That's proposed for 2029. And this is to sell for shipping. As I say, methanol's quite a big thing in shipping. And you would need 4 such plants to supply the whole rail industry. So, kind of one in most of the states. And you need about 5 million tonnes a year of biomass to make that much DME. And that equates to 15,000 tonnes a day, or about 4 train loads. The little train on the right, it used to run in Albany, run to Albany, Western Australia, narrow gauge, so it was a pretty small one. But yeah, a mainline train, you'd easily carry nearly 4,000 tonnes to each plant. So conclusion, a diesel can be net zero. It's going to cost a bit more, and the pros for a DME or methanol are that it is net zero if made from biomass. It could be used on existing locomotives with a few modifications to injectors, pumps, different tank. It's much easier to store and handle than liquid or compressed hydrogen. And it's not cheap, but it is cheaper than hydrogen or synthetic diesel. So is it a viable path for the Australian industry? Rail demand would be sufficient to get this going as an industry, whereas with hydrogen, you really would be looking at, you need other industries to push it, to create the, just that, what's the mass? The critical mass to get it going. Your ecosystem would require methanol production, sources of biomass, and rail links to the, this is taking away my surprise ending, sources of biomass and rail links to production facilities. If somebody decided we really will go this way, then you could have it up and running by the early 2030s, and maybe it would carry us through to the mid 2040s, when by that time battery technology, and there might be other technologies, might be a lot better, and you could truly electrify all of the rail, all rail systems. So this is a kind of a concrete plan you could present to government. Government don't really like hearing people just come and bringing them problems and asking for a solution. They like it when you take a solution to them and say, hey, we could do this, but we just need a bit of help. And if it worked, it'd also have export potential. Other people want to do it. So my conclusion is, don't send your diesel to the scrapyard just yet. And that's the end of the talk. Thank you.
Great. Thank you very much, Frank. A very interesting thought around what's going on. I mean, it was a good point, obviously, early, that diesel supplies are maybe not quite as rock solid as we once thought they were. So what sort of alternatives are there floating around? We've got a few questions. I've got a couple of questions from a couple of different sources, so we'll run through a few of them. One of them was around the methanol. How much additional water supply for wood production if Australian locomotives move to this option? I mean, wood production from softwood plantations, are they sort of heavy in water usage? Is that potentially an issue?
I have no idea. I always assumed that forest just grew from rain, but I don't know that.
No, that's a fair enough, mate. And the other question is talking about green hydrogen from electrolysis. Is that achievable, you think, by using wind panels, solar panels, wind turbines, that sort of thing? Or, yeah, are we still looking at using, the grid as it is?
Well, it could be both. I mean, the whole idea is that you're using renewable energy. So, well, like, for example, in like Fortescue over in Western Australia has been looking a lot at hydrogen, and they've been putting in solar farms and so on to and wind turbines to create the electricity to make the renewable hydrogen. There's I don't know where it's at. There's a proposed plant to make ammonia in Western Australia up near the Pilbara using renewable energy. So I'm not sure it's up to at the moment. So there was a lot going on, like a lot of talk back in the 2019, 2020, and I just noticed nothing's really advanced since then. But yeah, there's certainly all these plans for making a lot of hydrogen from renewables, but it turns out to be very expensive.
Yeah. No, thanks, mate. Another question I've got here: are there any specific safety risks that you're aware of? Let's look at the DME methanol option compared to current handling of diesel, which is relatively easy to handle from a risk perspective. Does methanol create new risks for the industry that they'd have to manage?
Methanol, it's got the pluses are that it's water soluble. So if you go and spill methanol and it goes into a creek, it's gonna wash away, and it kind of biodegrades. But at the same time, it is a poison, and you don't want to be drinking it.
Yeah.
You don't want to be exposing people to it directly. So I mean, methanol's not as bad as ammonia in that ammonia being a gas, when it escapes, it's really hazardous. Like you would not want to be in a tunnel where there's an ammonia spill. Whereas methanol, if you're not actually drinking it, sticking your hands in it, you're probably okay.
Oh, great, thanks, mate.
Also on the fire side of it too, it's not super explosive, but it will burn, and because one of the disadvantages of not creating soot is it burns with a fairly invisible flame. So you do have to be careful when it's burning because it's hard to see the flame.
Right. All right, thanks, mate. Another question here. If the rail industry adopts the do nothing approach, what will the industry pay in government pollution penalties? And is there a point where the penalties that are being paid to the government start to outweigh the costs of actually converting to, say, methanol or an alternative fuel?
Look, I don't know the overall figures, but see, at the moment, the price of carbon credits, I could be wrong in saying this, it might be $75 a tonne or something. It's not too high, but like previously, there were a lot of schemes which were pretty dodgy for creating carbon credits. And when they cracked down on that, it just reduced the amount of carbon credits available. So that starts to drive the price up. And as more people, as more companies are forced to be buying carbon credits, it's going to push the price up. So that's really the problem. So I think it's something that at the moment the operators choose to live with it because they haven't really got a choice. But yeah, the risk is that in the future, that price is going to be much higher.
Thanks, Frank. Another question we've got here is surely comparing to ethanol or other alternatives, converting a diesel electric loco to battery electric, as is being sort of looked at by a few places, is probably the easiest solution. Would it not be easier just to create bigger battery tenders, longer battery tenders, and just do it that way?
It can, yes and no. It depends on the application. Like a battery tender is probably going to cost you like not the same as a loco, but probably 80% of the price of it, because it's not just batteries on it. It's got to have a refrigeration system, a system to keep the batteries at the right temperature. And there's other auxiliaries and things. So it ends up being a reasonably expensive exercise. It's not just stacking a pallet of batteries on a tender. And I know some people have looked at this. And the other thing is, and I know in the Pilbara they're looking at it, but very often you're constrained with the length of trains when you've got passing loops. Yes. So everything you add to the train, like they're not right at the limits, but as you start to make your train length longer, suddenly you start to have to reduce this, your payload, take drop wagons off, which is not really good. And the other thing is a tender can't do regen. So every loco on the train, when you're going downhill, you're regenerating, you're recovering energy. That's pretty important, because being able to recharge your batteries is it's a pretty big part of it. So by having a tender, you can't recharge it unless you do put motors on your tender and traction equipment, all the rest of it, in which case it becomes the same price as a loco.
Yeah. Like the old cabless locos that used to be around for a little while over here in Australia. There was a few of them floating around, same sort of thing. Another question we've got here is, what's the range comparison currently between BELs and your methanol options, noting that DME and methanol are less than half the diesel equivalent?
Well, if you just stick one tanker on the train, you'd be able to go from Melbourne to Brisbane, say. And for trains that currently going from, like say, the East Coast from Melbourne to Perth, or Sydney to Perth, well, really from Adelaide to Perth, they already use tankers on the trains so that they don't have to stop on the Nullarbor. So you've already got one tanker there. You're probably looking at having two on the train. So it's not a big difference. So I think the extra range is not great, but it's not a plus that you have to put an extra tanker on, but it's not insurmountable. Whereas to carry that much energy in batteries, I think I have to look it up. I did put it in a previous talk, but I think I said a 1.8 kilometre long train, you'd be looking at 600 metres of it being batteries. Ooh. On tenders, and that was back of the napkin calculation, but it's about that.
Yeah, and obviously then you come back to that payload discussion, don't you? That the efficiency of the train is not improved by losing a third of it to battery storage. So that's certainly an issue. And the question I've got here is about setting up such an ecosystem as you've described. Setting up something like this is quite complex and would require coordination right across the industry. In your opinion, where would be the best place or rail application to start, or even trial bringing this sort of thing in?
Well, I mentioned that one at Bell Bay in Tasmania. Mm-hmm. So, there's a rail line there. As I say, they're making it for shipping, and I don't know what stage they're up to. All these things are hard to get going, but whether they've got contracts to sell it methanol to shipping, I don't know. But you've got one there already, and I suppose you'd be. And I think they were looking at another one up in Gladstone as well, and that was even further down the track. But like Gladstone's obviously in an area where there's plenty of railway lines. You've got sugarcane with waste and so on up there. Yeah, I have to admit, I haven't looked into this. I haven't done the business case for this. This is a fairly high level look at it at the moment. But
you're probably looking at something along the lines of a closed network, or certainly a closed operation would probably be best, rather than your open intermodal initially, and then looking to, like if you had a coal operation that basically ran from balloon loop and going round and round in a circle, would probably be an ideal starting point. And so Gladstone might be an option if that came up.
yeah, I guess the one thing is like with coal, it's kind of more intensive in that you got a mine with a conveyor going to a balloon loop, whereas forests are big spread out things. So there's obviously well, obviously they harvest wood chips and things at the moment. But actually, just on pricing, I noticed the price of coal, I think it was about $125 a ton. Price of wood chips is $270 dollars a ton. So you can see it's more expensive because it's harder to get.
Mm.
There's more work goes into gathering it.
Here's an interesting question. What about converting existing locos to electrification, so overhead wiring, and then strategically starting to electrify sections? So even if you turn locos into those sort of the hybrid diesel/electric locomotives that do exist in the world, and then progressively rolling out electrification, do you think that would be an option for Australia?
It's just that electrification is very expensive, and that's the whole reason for looking at batteries. And I've said that hydrogen is very expensive, but it's still cheaper than electrification. Well, just generally thought to be cheaper than electrification. So, yeah, whether you'd bother, yeah, I know. I think it's an expensive way to go.
Yeah, I think too in Australia, one of our biggest issues is that two capital cities run on completely different electrification systems, and the rest of Australia is now going for is 25 kV AC. So we've got three different systems around Australia, and that alone makes it complex. Moving on, we've got plenty of questions, so I'll keep asking. Next one is, do you see battery technologies like solid-state batteries, which Toyota are going down the road with, changing the range issue? They've got faster charging, greater stability. Do you think that solid-state batteries could come into play?
I'm getting questions about batteries, but this talk was about fuels. But anyway, no, well, I think battery technology it is getting better, and I think we can expect a doubling in energy density in the next few years, but how far they'll go, and don't really know. So like solid state batteries, Toyota's been promising them since I think 2015, and they still haven't really delivered. Whereas your conventional LFPs and so on, they've developed a lot. LFPs used to be the low energy density battery, and now they've kind of caught up to where NMC was a few years ago, and NMC's gone further. So yeah, it's because you've got the automotive industry there and storage applications, batteries are really getting a lot of development, whereas like say with hydrogen, there's nothing really driving it. Like it's government funding driving it, and that's all. You haven't got an industry that's you haven't got the sales driving it, and I think that's what's making batteries get better, that they're selling a lot.
Yeah, it's making that critical mass point where it actually becomes viable, and getting to that point can be quite difficult. Another question I've got here is, are there other sources of bio-waste that could be used instead of wood products?
Yeah, heaps. My garden. Got a green bin goes out. Well, yeah, I guess there's all sorts of agricultural industry produces bio-waste. There's there are many sources. That's all I can say, really.
Yeah. Okay. No, that's great. Thanks, mate. Another question here is, one of the issues that's not often considered when looking at batteries and other technologies such as the ones you're describing, is the cost of actually the manufacturing the batteries, solar panels, setting up these facilities, et cetera, et cetera. How does that all add into the equation? So, you're talking about creating ethanol plants. Obviously, there's a lot of greenhouse gases that are produced in the manufacture of these plants. Does that sort of start to play into this discussion as well?
Well, see, what I said with the methanol, it's all made from the biomass, and yeah, under the current rules, biomass counts as net zero because you're making stuff that grows again. So yeah, the plants, they are emitting energy. With the solar panels, everything, yep, there's a cost there, and a part of it's that being intermittent, you're not producing constantly, and that's where that tends to affect your amortizing the capital cost because you're not in continuous production, but it's still believed that it's going to be relatively cheap. I'm not going to argue the government's position on whether renewables are the cheapest form of energy, or at least not on this forum, I won't. But at least in theory, they're supposed to be cheap in inverted commas.
So do you see ethanol, for example, methanol, for example, as a good short-term solution, or do you see it as something so short-term, as I'm saying, sort of that 10 to 15 year mark, or do you see it so that would sort of bring a lot of existing locomotives to the end of their life cycle, or do you see methanol as something that is a much longer-term solution and a future solution, even for new locomotives?
I see it more as just being the short-term solution. As I said, through the 2030s up to the early 2040s, and then you're waiting for the newer technologies, which are going to, with the better batteries or whatever's coming next.
Okay, thanks. Next question I've got here is what are the current and projected challenges around producing, storing, and distributing these fuels? So let's talk about methanol. So what do you think are some of the biggest challenges around producing, storing, and distributing these?
I guess just the capital investment of building the plants. I can't remember off the top of my head what was the cost of that plant in Bell Bay, but it was pretty significant. It was I just cannot remember the figure, so I won't take a guess. But yeah, it's capital investment to start things off. And as I say, we had a methanol plant. It wasn't just closed down; it was shipped off to the US where natural gas is cheap. So the equipment's gone.
Right.
And that's why Australia's got no fuel refineries, because it's the capital investment to build a refinery. So
yeah. What's the distribution like for methanol? Is it any more complex than distribution of diesel?
No, just put it in a tank on a truck. It's not good for aluminium. It corrodes aluminium, so you wouldn't be using aluminium vessels. But and the other thing is it's roughly half the energy. Well, it's less energy than diesel, so you have to carry bigger volumes of it around the place.
Right. Another question here is production of fuel from direct air capture of CO2 likely to become viable as a technology as scale improves? And can this fuel be directly substituted into diesel engines? So fuel created from direct air capture of CO2.
Well, you've got the likes of BMW investing in it, so that they must be thinking, yes. I cannot see how it could possibly work.
Okay. Well, what's your thoughts on that?
Well, just that the amount of CO2 in the air is actually quite low. So you need to capture an awful lot, you've got to process an awful lot of air to get that CO2. It makes more sense to be taking CO2 out of, the exhaust stacks of, like power stations or where they make cement. There's a lot of coal goes into making cement, and you could capture carbon from there. Obviously, that's not renewable. That's just capturing carbon, CO2, which would otherwise go to the atmosphere. But I think you need a concentrated source to be getting it from the air. Is just you just have it's just a huge amount of energy goes into getting it, I think.
Right. All right. No, that's interesting. Thanks, Frank. Well, I think we'll call it there. So look, thank you very much everyone for your attendance today. And I'd also like to thank Frank Santo for his presentation, a very interesting one, lots of questions, which was fantastic. Please keep an eye on our webpage and on your emails as they come through for our next webinar. But until then, have a safe and wonderful day, and we will see you next time. Thank you very much.
Thank you.